Hello everyone. Today we will be discussing the few questions related to the Naveen and Jokerman book. This is the first question. Prove that an integer is divisible by 3 if and only if the sum of its digit is divisible by 3. Prove that an integer is divisible by 9 if and only if the sum of its digit is divisible by 9. Let us suppose n be any number which is equal to a0 a1 up to ak be the decimal representation of an integer n. Thus, n can also be written as in decimal form ak plus ak minus 1 into 10 plus ak minus 2 into 10 square up to so on up to a0 10 raised to power k, where ai is from 0 to 10. We know that since we can also write 10 minus 1 is equal to 9, so we can also state as 10 is congruent to 1 mod 3. Thus 10 raised to power k is congruent to 1 raised to power k congruent to 1 mod 3. Let it equation 1. Also n can also be written as n is equal to a0 into 10 raised to power k minus 1 plus up to so on up to a k minus 1 10 minus 1 plus a k 10 raised to power 0 minus 1 plus a k minus 1 plus a k minus 2 up to so on up to a0. Now from 1 we can write 3 divides a raised to power k minus 1 for any k belongs to positive integers. Therefore all the summands before ak are divisible by 3. So 3 divides n. This implies that 3 divides ak plus ak minus 1 up to so on up to a0. And 3 divides ak plus ak minus 1 plus up to so on up to a0. Then it also divides n. Similarly, for the case of 9, we have just to replace the divisor of 3 by 9. As in the same case, let n is equal to am minus 1 up to a1 a0 in decimal digits, so that n is equal to am 10 raised to power m plus am minus 1 10 raised to power m minus 1 plus up to so on up to a1 into 10 plus a0. Now we can also write as n as am into 10 raised to power m minus 1 plus am minus 1 10 raised to power m minus 1 plus up to so on up to a1 10 minus 1 plus am minus 1 up to so on up to a1 plus a0. In this what we have done, just simply in this n is equal to am 10 raised to power m, we just add am and subtract am. Similarly, all the terms we added and subtracted, and we take the subtracted term common as am and it is written as 10 raised to power m minus 1. We know that 10 is congruent to 1 mod 9, so we can also write it as 10 raised to power k is congruent to 1 raised to power k congruent to 1 mod 9. So from above discussion, 9 is divisible by 10 raised to power k minus 1 for any k belongs to positive integers, and then we will sum before am and which are divisible by 9. So 9 divides, and this implies 9 divides am plus am minus 1 up to so on up to a1 plus a0. Now here is the second question. If p is any prime number other than 2 or 5, prove that p divides infinitely many of the integers 9, 99, 999, 9999, up to so on. And if p is any prime other than 2 or 5, then prove that p divides infinitely many of the integers 1, 11, up to so on. For this, first what we will take as 9 k minus 1 times 9, which is also is equal to 10 raised to power k minus 1, and 1 k minus 1 time can be written as 10 raised to power k minus 1 by 9. Let p be a prime different from 2 or 5. Then let L is equal to m into p minus 1. Then for any integer m, 10 raised to power L is congruent to 10 raised to power p minus 1 whole raised to power m, which is congruent to 1 raised to power m, which is congruent to 1 mod p. This shows that p divides 10 raised to power m raised to power p minus 1 for all m greater than equal to 1. For any prime p not is equal to 3, thus we can show that p divides 9 into 10 raised to power m into p minus 1 minus 1 by 9. And therefore, p divides 10 raised to power m into p minus 1 minus 1 by 9, as p does not divides 9. Note that for any number to be divisible by 3, the necessary and sufficient condition is that the sum of the digits should be divisible by 3. This is because the number can be written as ck 10 raised to power k plus ck minus 1 10 raised to power k minus 1 up to so on up to c1 into 10 plus c naught. Then ck into 10 raised to power k minus 1 plus 1. In these above equation, we can subtract 1 and add 1. Plus ck minus 1 10 raised to power k minus 1 minus 1 plus 1 up to so on. So which is also congruent to ck plus ck minus 1 up to c1 plus c naught mod 3. As 3 divides ak minus 1 for all k, this shows that the 3 divides 1 1 1 up to 3m times for all m greater than 1. Now the next question is, if 2 raised to power n plus 1 is a odd prime for some integer n, prove that n is a power of 2. Since given that 2 raised to power n plus 1 is odd prime, so for any integer n, then we need to prove that n is power of 2, say n is equal to 2k. Let us claim that no odd prime divides n. If possible, suppose that an odd prime p divides n, then n is equal to pq, where q is greater than 1 and less than n. So we have 2 raised to power n plus 1 is equal to 2 raised to power pq plus 1, which is also equal to 2 raised to power q whole raised to power p plus 1. And here we will use the identity, which is equal to 2 raised to power q plus 1 into 2 raised to power q into p minus 1 minus 2 raised to power q into p minus 2 up to so on up to 1. And also we know that 1 is greater than 2 raised to power q plus 1, which is also greater than 2 raised to power n plus 1. So this implies that 2 raised to power q plus 1 divides 2 raised to power n plus 1 properly. And which also implies 2 raised to power n plus 1 is not a prime. This says that n is a power of 2. Now the next question, as we have to evaluate the value of summation j going from 1 to infinity mu of j factorial. We have to find the value. So here we have summation j is equal to 1 to infinity mu j factorial can be written as, by expanding it, mu into 1 factorial plus mu of 2 factorial plus mu of 3 factorial up to so on up to infinity. And we know mu of 1 factorial is equal to mu of 1, mu of 2 factorial is equal to mu of 2, and mu of 3 factorial is equal to mu of 6 up to so on up to, in the case of mu n factorial, which is equal to mu n factorial. And we know mu 1 is equal to 1, mu 2 is equal to minus 1, mu 6 is equal to plus 1 up to so on. All the terms after mu 6 will be 0. So we get the desired result as 1. So summation j is equal to 1 to infinity mu of j factorial is equal to 1. Now here is the fifth question. Find the least positive integer x such that 13 divides x square plus 1. Here we have to check the 13 divides x square plus 1. for the value of least positive integer for x. So first of all, we will take the least positive integer x is equal to 1, and we get 13 divides 1 square plus 1 means 13 divides 2, but this case is not possible. So we will put x is equal to 2, then 13 divides 2 square plus 1, which is equal to 13 divides 5, but as we know 13 does not divide 5, so this case is also rejected. Now put x is equal to 3, we get 13 divides 3 square plus 1, which is equal to 13 divides 10, and which is also not possible. Similarly, the case of x is equal to 4, which is also not divisible by 17. And in case of x is equal to 5, we have 13 divides 5 square plus 1, which is 26. So 13 divides 26. So the condition is satisfied. Therefore, x is equal to 5. For the value of x is equal to 5, we get the least positive integer that satisfies our condition of 13 divides x square plus 1. Thank you.